Thank you, Dario, for your introduction. And I would like to say upfront, I really much appreciate the work which Euro-BioImaging is doing. I think this is really important for the community, so I'm more than happy to present here today. My task was to tell you something about how we optimize preclinical MRI. This is a pretty bold term. So I have a few slides covering this, but there are also excellent upcoming speakers. And I think we can cover together this topic much better. But I will more particularly tell you a little bit more about a recent software development in my lab, which is about the effective removal of low quality outliers from large MRI data sets. All right, so when I started my lab 8 years ago, I actually thought a lot about how to organize this lab, and this is really in line with this bold title, how to optimize preclinical MRI, because my lab is doing a lot of preclinical MRI, but in the context of experimental stroke. So we came up with two main pillars, which you can divide again in two. So in total 4 pillars, and this is software pipelines, which do something for us in an automated fashion, and research data management, which sounds like a rather boring topic, however, of utmost importance. And this is related to how we can openly access or make our code accessible, our data accessible, and finally have a workflow to make data really reusable for others, but also reproducible. And you see there is a missing topic here, and this will be the QC later on. Okay, but very briefly, for sake of time, what is this data management and multimodal workflow about? So we have in the past, and this is all published, established workflows for how we record metadata in the lab, which is done by an electronic lab book. There are multiple versions out there. We made our own tailored towards our applications, which is not only MRI, but also behavior tests, histology, you name it. And this is all electronic data, so you can only record it in an electronic database and not handwritten. And this database has a lot of nice features, which you know from other databases, like you have different user management ways. You can block, you can make blinded experimentations that people don't see, what they should not see, for example, if it is a treatment group or not. You can have statistics on that and so forth. We have standard operating procedures. Sounds very trivial, but in the end, this is not trivial at all, especially when it comes to keeping them updated and keeping them actually used by people in the lab, especially if you have a frequent turnover of students, as I do. So you can call me pedantic. I even have SOPs for the students on how to save data. Yeah, and this saving data is a good word to cover for the next slide, because we have a workflow established, and this was published 2 years ago in Scientific Data, on how we organize our data workflow. We have a central identifier for every mouse or every animal, if you wish, and this is very important because this identifier will be in every file related to that animal. So whatever I search on the computer, I will search for this identifier. Yes, multimodal data, and this is all stored in a standardized folder form structure. Yeah? So if you download any data set from us, you will always find this structure called Yoda structure from computer science. And this gives not only us as humans, but most importantly, computer the way to iteratively search through these data sets. And there is backup. I will not go into detail for that, but there is also version control. We use DataLab. There are other software packages out there. And this is all completed by publishing the data on a public repository for publication. Right, and the second pillar were automated software pipelines, and we call this atlas-based imaging data analysis. Has grown through the past years to a real family. This is also all published, where you have pre-processing pipelines for mouse and rat anatomical, functional, and diffusion MRI, for some histological analysis and also brain network analysis. Okay, so this was a very brief how this is organized in my lab. And you see here the missing pillar, and this is quality control, because we realized actually in a very brutal way that when we want to reanalyze our own data, covering hundreds of mice, we have one main issue, which is to now find out how we can exclude outliers. What is an outlier? So many questions. And of course, this was not done alone in my lab. Actually, the idea was born together with Giovanna Yelakva as part of the European Society of Molecular Imaging standard group. So this was really like people coming together, and we started small, but it actually grew a lot. So in the end, we involved 8 countries and data sets from 23 data sets to really work on this automated pipeline. And to give you now a very brief idea of why this is so important, you see here examples. So these panels are from 4 mice, and this is resting state fMRI data. And you are now about to judge which of this data set is of better or lower quality. And I will give you no strict criteria. This is just your own subjective judgment. And of course, this is complicated if you not have looked at this, and one will say, okay, I have not seen the complete data set, so far so good. But our automated pipeline in the end voted that these upper 2 examples are actually of good quality, so it's not an outlier. But this one here was labeled as an outlier. And you can now think for yourself if this was yours. And let's do another example for diffusion MRI. This is now differently organized. You see always 2 panels from the same mouse. This is diffusion weighted imaging data set and the related processed file, which is an fractional anisotropy map. So it's a quantitative map from the same mouse, same slice. The other mouse, and so on and so forth. And of course, you can make up your mind what you think now is of worst or best quality. And I think that was a bit easier because we all have seen that this has a lot of ghosting, and we would have labeled this probably all as a potential outlier. But you see that also our automated algorithm also labeled such an image, which rather looks pretty good, I would say, as a potential outlier. And we will now go through the details why actually we as humans are not really suited to go through hundreds of these images and make really reasonable judgments. Okay, so the pipeline consists of 3 pillars. Very briefly, we have input files, which can be Bruker files, Nifty files, bits data, you name it, no DICOM. We have automatic parsing of the data, which extracts just features of the sequences. This is all mapped and plotted if you need this for data analysis later on, and saved in CSV files. And the second stage is the more important stage, where we get to the feature extraction. And features in our case are very simple. Of course, you can use a lot more image quality features, but we chose only these major 3, which is signal to noise ratio, temporal signal to noise ratio for resting state, and motion or ghosting artifacts. Okay, to calculate SNR automatically again is a topic on its own, which could cover 15 minutes, because to come up with something which works robustly for a lot of data sets is not that simple. In the end, we came up with something like this. We find automatically like the center of intensity of this image, which we put a sphere in, and then for the noise, we set in the corners boxes. So this is SNR. There's also another method which we use in the paper, a little bit more complicated, using the raw histogram data of the signal. But in the end, this is only to show you that this SNR calculation, although it's done completely automatic, makes total sense. This is a pretty dark image of low SNR, and this is an image here of very high SNR. Okay, for TSNR as humans is rather difficult to see because from the real image, you don't see it exactly. You need the time series. And as a T map, so to say, of the SNR, you see it much better. And this is also what the algorithm is using. All right. The third pillar of this features were ghosting and motion artifacts. And again, this is not that simple to calculate automatically. But we came up with a measure of mutual information, which is actually calculating from one slice to the other how much they both match with each other. And you see that if there is ghosting, we can see this very nicely in the mutual information. And you can track this over time, and then you see over time also in this time series, for example, that if there is motion or if there is no motion. All right, and all of these is compiled into CSV files again for results, and then we come to the judgment. The judgment is done by combining statistical and machine learning algorithms. It's 5 of them. For sake of time, I don't read them because I also don't have the time to explain all of them. But we covered, or we chose 5 simply because they all have pros and cons, and some can see, so to say, differences much better than others, in particular sequences and so on and so forth. So it's kind of a mixture. And you get out a CSV table where you get this labeling of this could be a potential outlier. And if all of them say this is a potential outlier, you would have a majority vote of 5. All right. So, of course, we had the big task to validate our tool. And this was, again, oh, I'm repeating myself, this was, again, not that easy, simply because there is no good gold standard. Why is there no gold standard? We asked 5 experts to judge the data sets, anatomical diffusion and functional. And this is plotted now. Here's a heat map for Fleiss kappa score. Fleiss kappa score is listed here. Yes, you can see we, in average, reached 0.2. It's here labeled as fair, but fair is not good, you know. It should be like almost perfect or substantial at least. We can sum this up. We have a low to moderate inter-rater agreement. So in other words, the experts really had different opinions about what is an outlier and what not. If we then later in a second step gave these experts the pre-sorted files by our automated tool, this was much better. So the agreement was then 72%. Okay, then we did very simple validations of just checking that the SNR increases over field strength and that we can actually detect this automatically, or other stuff like by adding noise or adding motion, that we are also able to detect these data sets which had this aberrant noise signals. And is it really relevant now to remove these outliers? Is it all necessary what we are doing here? And this is now one example from functional connectivity. We have more examples in the paper. You see here two examples. I have to go back. You see here 2 examples. And this data set got a majority vote of 5. So speaking that this is really an outlier. And this data set got an outlier of, a majority vote of 0, meaning this is kind of a normal data set. And you are asking now why, because from the SNR, it cannot be the case. So we look at the time series, because this is functional data, looks rather normal until the end. Let's see how it develops for the second data set. Looks also rather normal, or actually to the end. And this is the key. Here in this data set, in the first one, we had actually at repetitions 1 to 5 or something. There was something odd with the scanner, maybe the gradients went off. And by eye, of course, by just looking at one slice, the human radar would not have seen that, yeah? But the automated algorithm saw this, and that's why I labeled it also as an outlier. Yes, coming to the end, all of this is publicly available on our GitHub page. You're more than welcome to check this out, ask us, collaborate with us. There's documentations on this. I thank the people who work with me on these projects, also the funding institutions. And I have open PhD positions, so if you have a good master student, please forward to me. Thank you for your attention and happy to take questions.